The Big Bang and Cosmic Microwave Background: Challenges and Unsolved Problems. Though the Big Bang theory has many observational evidence to support the claim, there still exist unsettled questions that challenge the basis for such a model. Today, we will explore some of these issues and touch upon possible solutions. What we will cover: some key technical issues surrounding the Big Bang theory involve general relativity. Einstein provided one of the most successful theories ever devised, general and special relativity. But, as we will touch upon, it appears to only be a special case and doesn't work when the math is pushed too hard. Problems with matter. There are asymmetries that must be addressed. Our predictions do not match what we actually see. And is there a grand unified theory, something that will save us from our own mathematical demise? General relativity breaks down very close to when time just began. Pure general relativity gives the wrong predictions for the behavior of space-time due to quantum effects taking over. In other words, we need a quantum gravity equation. But limitations are very well known. Quantum mechanics deals with the behavior of the microscopic realm. And general relativity's domain is the very large or macroscopic realm. Both of these theories have been extremely successful in their own rights. But there is a piece of the puzzle missing, because the two theories don't converge, and we know they must. General relativity infamously fails for objects such as black holes. This is a huge problem, because it is predicted that the moment of the Big Bang was in a similar state, known as a singularity. In layman's term, a singularity means we don't know what happens. Somehow there is an infinite density inside of something with zero volume. General relativity breaks down at approximately 10 to the minus 34 seconds. At this point, all of the mass and energy of the universe was the size of a grain of sand. Problems with matter. There is a prevailing idea in physics conservation. Essentially, all things must be created or destroyed in knowable or calculable amounts. Think of it as balancing your checkbook. If you keep track of all your expenditures, you can predict how much money is left in your account. Well, the universe is stubbornly cooking the books, and we haven't been able to figure out how. For instance, when a particle is produced, it must have a twin with opposite properties. For example, a spin up and down particle. This is called conservation of spin, or a negative and positive charge. That way, total charge adds to zero, which is what we started with. This presents a problem, since particles will arise with opposite charges. A particle and its antiparticle twin are known to immediately be attracted to one another and annihilate. This will produce photons, or light as it is commonly called. So the issue is, why did any particles at all survive? Another identified issue surrounds magnetic monopoles, a magnet with only a north or south pole. We are very familiar with dipoles, or magnets which have different polarities on each end, but have never encountered one in which we could break it in two and only preserve one pole. Instead, you just get a smaller version of the dipole you started with, still with its north and south poles intact. A grand unified theory. The ultimate goal for scientists is a mathematical framework from which all observed phenomena can be described. As we have learned, we aren't there yet, but nonetheless we have made great strides. Some intriguing ideas replace our current point-like objects with vibrating one-dimensional strings. These strings can become all the matter we see, just by changing how they vibrate. It is the focus of my project to explore these fascinating frameworks and give some overview. I implore you to get interested in our cosmic origins, and maybe you may lay down the next important steps.